So hopefully you've already watched the video about what we mean by a free body diagram. You will be required to draw and label an accurate free body diagram for every numerical problem on the test. So I highly recommend that you get in the habit of drawing these for the problems that you are solving on the homework. Again, the reason I'm requiring it is because it's so essentially helpful in writing equations and solving problems. So I want to take a few minutes to go through some examples of free body diagrams. These are labeled the quizzes that I share in class when I'm face to face with my students. So just as a reminder, free body diagram, FBD, is how we represent it. We draw a dot to represent the object, and then we draw each individual force vector on that dot, and we label it. So our first question. Read through this. I pause for a minute, read through it, choose an answer, and then I will walk through the answer. So this problem isn't technically asking us to draw the free body diagram, but I'm going to as part of answering it. We're told to ignore air resistance. We want to know what force or forces act on the ball. An important part here is this statement: as it moves through the air just after leaving the horizontal ramp. So our free body diagram, we need to know where in its motion the object is in order to correctly account for all the forces. We know this ball, it tells us it rolls down the ramp, it goes, it turns, and then it leaves the ramp. Now, granted, as it leaves the ramp, it's going to have an initial velocity. Its motion from there will be projectile motion. The ball will continue moving right horizontally at the same speed, but it will speed up towards the ground because of gravity. So my free body diagram, if I draw my dot representing the ball, this problem is specifically asking, okay, the ball has just left the ramp. What forces are acting on it? So of course we have the force of gravity, because we always have the force of gravity. That represents the force of the Earth gravitationally attracting the ball towards the center of the Earth. Any other forces would be contact forces. The only thing this ball is now in contact with would technically be the air. And so the only other force that could potentially be acting on the ball would be air resistance. But this problem tells us to ignore air resistance. So in this case, at the time this problem specifically mentions, this ball only experiences the force of gravity. Now, as far as our options are concerned, the term weight is often used to represent another way of saying the force of gravity. The weight of the ball is representative of how hard the Earth is pulling on it. So A is the correct answer. This question gets at a common misconception. We do know this ball is moving. The ball has a velocity. But in our free body diagrams, I should write it this way. We only draw forces. Forces only. So we don't draw velocities in here. We don't draw the acceleration in here. Only the forces. So even though the ball does have a velocity, that velocity that it has right as it comes off the ramp is going to contribute to any projectile motion problem we solve, right? How far from the end of the ramp will the ball hit the ground? How high was the ball before it hit the ground? So that actually would take us back to this previous section where we talked about projectile motion. So free body diagrams, this portion is new. Just look at the forces, recognize what forces are acting on the object of interest in the problem. So let's do another example. Here is our next example. Again, go ahead and pause to answer. So I'm going to draw just a rough sketch. We have this sled. Initially, this sled is being pushed by the person. So it's moving, we get it going, but then she jumps in and the sled keeps moving, but it slows down and stops. Specifically this question, what forces act on the sled just after she's jumped in? Again, the period of time that is asked about is important. So this problem doesn't specifically ask for the free body diagram, but I'm going to include that as part of the answer because recognizing the forces is the first step in drawing the free body diagram. So I'm going to draw the dot that represents her in the bobsled because the problem is asking us about after she's jumped in. So the sled, of course, experiences the pull of gravity. Now, this pull of gravity would be on the combination of her and the sled, but we can allow that dot to represent her in the sled because they're moving together. So the force of gravity downwards is a field force. We don't have magnets, we don't have electricity, so we don't have to worry about those field forces. Any other force is going to come because of contact. We know the bobsled is in contact with the ground, so there has to be a normal force of the ground pushing up on the bobsled. So the ground being horizontal, normal force has to be up. That's the definition of the term normal in mathematics term. So it has to be perpendicular to the surface. Now, the third force comes from reasoning out that the sled gradually slows down to a halt. It stops. There has to be some sort of force that is giving the sled an acceleration. Any acceleration is due to forces. So if the sled is slowing down to stop, in my picture, I've shown the velocity to the right. To slow down, that means the acceleration has to be to the left, but acceleration is a result of a net force. So there has to be some sort of force to the left that is creating this acceleration to the left to slow it down and stop it. This force it has to be due to the contact between the bobsled and the surface because there's nothing else in contact with the bobsled. So the only thing we can really have is friction. We need to determine, in this case, they label it as kinetic friction, which is, of course, true because the bobsled is sliding on the surface. Static friction would be for an object not sliding, so that's why that's not applicable here. So after she has jumped in, these are the three forces acting on the bobsled. So gravity, normal force, and kinetic friction. So D is the correct answer here. It is common to want to put in a force of the push. That would be true if the problem asked us about the period of time while she is pushing on the bobsled, but not at the period of time just after she's jumped in. So even though the bobsled is going to be moving to the right when she jumps in, that does not show up in this free body diagram. Please ask questions as you're studying this. This portion of recognizing forces and drawing out the free body diagrams is extremely important. Let's do another example. Here is our next example. Go ahead and pause the video, determine your answer, and then watch the explanation. Okay, so my elevator, again, my elevator is my object of interest. So that's my dot. I know there's a cable pointing upwards. In our options, they have not labeled all of the forces. I'm going to go ahead and call this tension. A cable is essentially a big cord or rope. So if the elevator is lifted by the cable, that cord or rope has to provide tension upwards. We always have the force of gravity downwards. At the moment, I am not putting any effort into how long I'm drawing these vectors, but I obviously have to consider that when I'm choosing the answer. The important piece here, beyond the free body diagram. So the free body diagram, we have two forces. That's it. The cable itself is controlled by the mechanics of the whole elevator system. So there's no additional force of the elevator. So D is not an option. It's the cable itself that's lifting the elevator. There's a force of gravity downwards. Now we have to reason out what is meant by moving upward and slowing. This portion comes from the last section. If the elevator is moving upward, I would draw the velocity it has pointing up. Let me draw that better. The acceleration. I know this elevator has an acceleration because the problem tells me that the elevator is slowing. Whenever an object is slowing down, its acceleration has to point opposite to its velocity. So the velocity being up means there has to be an acceleration pointing downwards. Acceleration, according to our friend Sir Isaac, acceleration is caused by a net force. The value of it depends also on the mass. But what this tells me is the acceleration and net force are always in the same direction. So if I know the acceleration has to point down, then I know these forces acting on the elevator have to add together to give me a net force pointing down. It's the net force that gives the object, the elevator in this case, its acceleration. So the only way these two can add together and give me something that points down is if mg pointing down is bigger than the tension pointing up. So coming back to the problem, I know the net force can't be zero. Otherwise, there would be no acceleration. So my options to choose from are A, B, or C. In here, we have to assume these vectors are drawn to scale. So we want to look for the one where the downward arrow representing mg is bigger than the upward arrow representing tension. That is option C. Option A, the upward arrow is a bit bigger than the downward. B, up and down look equivalent. So C, the downward is a little bit bigger than the upward. So C must be the correct answer. Again, please ask questions as you're going through the homework. Practice drawing free body diagrams. When it comes to seeing your free body diagrams, I am not going to judge you or grade on them drawn perfectly accurately to scale. In fact, you're going to find as I do examples that I don't really draw them to scale, but I will reason out what direction the net force needs to be in, so that when we set up our problems and write out the mathematical equation describing F equals ma, that will help to do so. Let's do one more example in this video. I do have a few more examples, so I'll just make another video with that. So question, again, pause, determine what you think the answer is, and then watch the solution. All right, so we have our ball. It's been thrown straight up. So as initial velocity upwards, we know it's going to rise in the air and come back down. We want the free body diagram just after the ball has left the hand. So essentially, at this moment where we say it has this initial velocity, right under the influence of gravity. So my free body diagram, of course, we have the force of gravity. So the ball, the dot represents the ball. The force of gravity is acting downwards. Any other force would be due to contact. We're ignoring air resistance, so we do not need to add an arrow to represent that force. Now, of course, that arrow, well, it may not be of course to you. Air resistance, if we were to include it, would point downwards as well because it opposes the motion, so it's always opposite the velocity. That's just a side note. In terms of recognizing any other forces, that would be due to some sort of contact. Since the problem is asking about after the ball has left the hand, our hand is no longer physically in contact with the ball. Therefore, we do not draw that force. This is our free body diagram. So D is our correct answer here.